All right. Hello, everybody. This is tutorial 1 on Excel, and our purpose today is to utilize Excel to determine the enthalpy required for any process. Okay, so we're going to start first with the enthalpy required to heat an element or a compound, something like zirconium oxide, and this is what we will be aiming to do here. This is what we are trying to achieve at the end. Okay, so let me start from the beginning on a new sheet, and oops. So what I like to do always is that I write down my givens, and for starters, we're going to start with the CP. And remember, the CP, if you want to calculate the CP, it's a. You can say it's a times t power 0, yeah, plus b times t power 1 plus c times t power -2. Yeah. So this is the given. This is the first thing that we need to worry about. So you will find this from the appendix, and then you can find here 69.62, and then here this is 7.53 times 10 power -3. So I can just say here 7.53 times 10 power -3. Okay. And the same thing here, I'm going to just write here -14.06 times 10 power 5. Okay, so these are my values. Now there are several ways to integrate. What I'm going to do right now is just I'm going to basically integrate it myself. There are more complicated ways to do that. So for example, integration of at power 0 is going to be at power 1. And integration of bt power 1 is going to be b over 2 t power 2. And then integration ct power -2 is going to be -c t power -1. So that's it. So, oops. Okay. Oops. Let me just... I think it doesn't like... Yes. Okay. It just doesn't like this negative here. All right. Perfect. So what I'm going to do here, I'm just going to equate the values again. So this is the same value because the integration of the constant is just going to be the constant times t. And then here it's going to be this constant over 2. And then here is going to be this constant multiplied by -1. Perfect. So this now I got the coefficient of every constant in the CP equation. So I could say that this is, well, yeah, I can see that this is H. Okay. So the last step is to integrate through the range. So the temperature range. Let me write that here, T, and then I will say the initial temperature. So that's initial T and then final T. Okay, let's start first, for example, from 298 until, like the problem that we had in example 1. So this is example 1 here. Let me write that here. When you're heating from 298 Kelvin to 1400 Kelvin. Okay, so this is the given. All right, and I have this already, and then the enthalpy, the final answer. So that's it. So what I'm going to do now is that I'm going to substitute in these. Let me try and shift here because what I'm saying here is that these are also some kind of given. So the output is going to be at the end. Okay, that's it. So what I'm going to do is that I will start saying, so I can modify this one and I would say, okay, it's actually multiplied by t power 1. Like this, C7 minus B7. And that's going to be our range, okay? And then again, the same thing here. Let me separate this here, and then multiply C7 square minus B7 square. Why? Because it's t power 2. All right, and then last one here, this is d times -1. Okay, so I'm done with the coefficient. So I can add this here now, and I can say it's C7. I can write it C7 power -1, or I can just say it's 1 over C7. Let me just write it C7 power -1 minus B7 power -1. It's up to you. Perfect, that's it. So I have these three terms right now, and then the final h will be the sum of the three of them. I can say the sum, and then I can drag this here. Or I can say, sometimes I like to say this like this, and then comma, this, oops, and then comma, and then this. It's the same. We'll keep this one here. So this is my enthalpy, and the unit is in joules. Just don't forget your joules. Okay. So this is here the example 1, zirconium oxide. And if we want to determine what is the enthalpy required, it's going to be 80,000 joules. Okay. If you want to try to do example 2, let's try to copy here. Okay. What was the difference between example 1 and example 2? It's the final temperature, 2670. Okay, so this means that I need to remember that the range here is actually from 298 until 1478 Kelvin. And this is the value here. You can write that down here, for example. Let me see. So let me copy paste, and then I'm going to write the other range, which is 1478 until, I can't remember what was the, anyway, it was whatever plus this. So that was the alpha, and that was the beta. So alpha zirconium oxide has the range of has a range of 298 to 1478 Kelvin, and that's their constant. And then if you look here for the appendix as well for the beta, let's try to look there, and what would that be? Yes. So for this one, we don't actually have these two terms. Only we have this term here, which is 74.48. That's it. Perfect. And then I'm going to go for the initial here and then initial here. So what we can do, because it's two different ranges, I'm going to put it here, and then I'll put another one here. And this range should stop at 1478, because this is where the heat capacity is provided. And then we will start here from 1478 until our intended temperature, which is 2670 Kelvin. So we have two ranges that we're calculating on, T2 and then T2 to T3. And this is T1 here, and this is here T3. Okay, makes sense? All right, so what I'm going to do is that I can try to integrate as well the same thing exactly. That's exactly what I'm going to do. So what we can do here for starters, it's up to you what you can do. So what I can do right now is that I will get the enthalpy for alpha first. And look at that. It already automatically calculated it. It was 80,000, but since we're looking for a higher temperature range, 1478, it was 1400. So just once we change this range here, the enthalpy of the alpha range is already updated. Perfect. So what we can do right now is that we can just copy paste this here, and then let's try to see if this can work here, and then that will be deleted. And let's see if this is working here. Yeah, it's working perfectly. So here we have 74, which is the integration, the right integration, and it's the L10 minus K10. Okay, perfect. So the last thing here, this is the last enthalpy. So that's here, that's beta. Now you need to remember, do not forget this. Oops. Let me put it a little bit too down. Okay, perfect. Now remember that there is an enthalpy alpha to beta, which is also in the appendix. And if you look at it, it's 5900. And this is, the unit is joules. So now we have this term here. That's the alpha enthalpy. And that's the alpha to beta enthalpy. And then lastly, that's the beta enthalpy. So if I'm trying to calculate the total enthalpy, I'm going to make sure that it's the sum of this, comma, this. Oops. All right, that's it. And then your answer here is 181 kilojoule. That makes sense? So this is example number 2. Do you see how easy it is? Now, this, I know the integration can be utilized with the MATLAB or other equations, but the best part about this is that you created your little program here, your little interface that you can play with anywhere you want. Like you can say, okay, I want to change this number. Let's make it 3000. It already automated this. Okay, or I want to change this from 298 from room temperature. I want to make it from colder temperature, so that will change things better. Or I want to make it from higher temperature, and that will update things more. So you created yourself a little program here, and you can update it. And the best part is that once you're done with one equation, with one program, you can easily produce it again and modify it accordingly. And trust me, once we're done with the enthalpy, if we're looking for the entropy or Gibbs energy, it's going to be probably exactly the same thing. Okay, so that's it. So your task is to solve these two problems using Excel, and yeah, that's it. And I'll put an assignment for that. All right. Goodbye.